such a great event. It's a really honor. And today, we're here to talk about tests. But I'm Daniela Petruzalek. I'm a principal engineer at JP Morgan Chase. And the inspiration of this talk is, okay, so we write the tests to ensure that our code is okay. But how can we ensure that the tests are okay? So this whole thing will be about a technique that will give you just that, a way to validate your tests, which is called mutation testing. But before getting to that point, of course, we need a few disclaimers. So mutation tests is usually a very colorful language, and we are going to talk a lot about killing things. So I just want to make sure that no production code was harmed during the making of these slides. I can guarantee you that any similarity to the real code is merely a coincidence. And of course, before getting to the core of the thing, I think it's important for us to revisit why do we do tests in the first place, right? So I usually like to say that tests are an insurance policy, and bear with me for a moment, because tests have two main finalities. One is to ensure that the code that you're writing does what it's supposed to do, which sometimes we refer to this as the happy path. Of course, the negation of that is also true. We also want the test to ensure that the code doesn't do what it's not supposed to do, or sometimes referred to as the sad path. And how does that relate to an insurance policy? Well, as software engineers, we should be free to modify the code, to refactor, to improve it, to extend it as we please. But if you don't have the guardrails of testing, if you don't have a good testing suite, you have nothing stopping you from going too far. But when you have a good test suite, you basically can go crazy, you go wild and say, oh no, I'm going to refactor this, delete that, and so on. And the test will tell you when you went overboard. They will break. So this is why the tests, as software engineers, they are your insurance policy, because they guarantee you that they didn't cross the line. Beyond that, tests are also design tools. And here, it doesn't really matter if you're doing like proper TDD, like as the traditional, I'm going to write my test first, doing my test case, then I write the code, make it pass. Or if you're more old school like I am, I write the code first and I write the test second. But in any case, the tests are usually the first client of your code. And at that moment, when you're first making your test and calling your code, you have the opportunity to think about your API and say, oh, wait, should I pass this value? Should I pass two values? Should I pass a struct? Should I return one value? Should I return two values? Do I have a side input? Do I have a side output? And so this is your opportunity to revisit the design. And based on my experience, what I noticed after so many years of career is that there's a very strong correlation between code that's easy to test and code that's easy to read / easy to maintain, which I also call good code. If code is not easy to read, easy to maintain, remember, we write code for humans. The machine doesn't care. So by having good code, you're making your life and your colleagues' life much easier. How do we typically measure tests? So there are two main metrics in the literature, and it's kind of confusing because we tend on a day-to-day basis to use them interchangeably, as code coverage and test coverage. But they are fundamentally different things. Code coverage is the percentage of the code that's touched by your test. If you have 100 lines of code and your test runs 50% of those lines, you have 50% coverage. That's very straightforward, very easy to reason about. Test coverage is a bit different. It talks about functionality, so it talks about your use cases, your different scenarios, how many of those are touched by the test. This is a bit more abstract, a bit harder to compute. So we're going to stick with the code coverage definition. And now this was just like for informational purpose. For the remaining of this talk, I'm going to use those two terms interchangeably, as we do on a day-to-day basis. And of course, as we know, the Go compiler makes it super easy to extract code coverage from your unit tests. So you can say Go test cover, you have a metric, or more recently, now you can use go build and go run with dash cover and use this to run your tests on top of that, and you can start integration test coverage. And then you can merge those and have a unified view. But you see, super easy to get coverage, but this comes with a problem. Because it's so easy to get this number, and this is the most obvious thing we can do, that teams and companies, they start to make covers. Oh, maybe we should have a target for that. Maybe that target is 60%, 70%, 80, 90, 100. Doesn't really matter. X% amount of coverage is a good thing. And someone says that, and someone says, oh, you know what? We can do it even better. Let's automate it. And let's put a rule in the CI. You cannot merge this code unless you achieve a 70% of code coverage. Yeah, there's a problem with that. There's something called the Goodhart law. A metric that becomes a goal ceases to work as a metric. So we are smart human beings, we're software engineers. If someone tells you, you need to hit 70% code coverage or you will not merge to master, you are going to beat that target. And now it's game mode. You don't care about the insurance policy anymore. It's 70%. And oh, I reached 71. I'm done. I'm done. Beat the goal. That's it. 70.1%. I'm done. Beat the goal. Over. And this also makes you test things that you wouldn't normally test, like testing the main function. How many discussions we have about that? Should you test main? Maybe. I don't know. Does that make sense for you? Oh, no. But I need those extra 5%. And another problem with that is that, as you see in this example, code coverage is very easy to fake. So this is a simple function, just a simple division. The only logic in this code is that it protects you from a panic by checking if you're dividing by 0. So here, compare to 0. If yes, return an error. If not, do the division. As simple as it gets. Remember, this is a toy project. We're just demonstrating concepts. And the thing is, can we achieve 100% of code coverage without testing absolutely anything in this case? The answer is yes. This test, I'm glad someone got it, this test will never fail. The only possibility of this test failing is if it raises a panic and we already got that covered. So you can run this as many times as you want, never fail, 100% code coverage. Oh, I don't trust you. Yes. Okay, let's see some code. I'm going to run here. And you can see here on the screen, 100% coverage. VS Code does the highlighting for us, so all lines covered. Can we fix that to have a proper test? Yes. Would be something like this. Let me just close this. This is a bit more a reasonable test. I still have a bug here, which is, this is a very suspicious case. Bear with me, this is here for a reason. But at least I have the happy path test saying, I'm going to divide this one by one, get one. At least it's checking, oh, no errors returned, and checking my expected result. For the divide by 0, I'm expecting the bad case, so I'm just checking that the actual error is coming. And if I run this, I still get 100% code coverage, but this looks more like a proper test. Hopefully you agree with me, otherwise the talk is over and we can all go home. Okay, so here I have one example, one test, and it's easy to see that this is bad. But what if you have 1,000 tests? How can you find the bad ones, right? And this is where mutation testing gets into play. So as I said before, mutation testing is a technique to find flaws in tests by introducing small mutations, small modifications, which we call mutations, to a program before running the test suite. And by small modifications, I'm saying things like this. I'm going to reverse Boolean operations or replace them completely together, like changing operators. In this case, I'm giving, it's somewhat like a biased example because I say multiply by division, plus to minus, but they don't need to be the symmetrical opposite. You can change multiplication to a minus sign, and this is a proper mutation. You can force Boolean expressions to be true or they're false. You can even remove complete statements like an else condition or, I don't know, the entire function body. And apply scaling to certain values. You have sometimes a constant. You make it, if it was small, you make it big. If it was big, you make small, and so on. All right, so these are mutations. In the literature, you can have infinite amounts of those. These are some common ones that appear in literature. And here's where the terminology gets very colorful and interesting. So remember, your baseline is all your tests are passing. And then you apply mutation, and you run the test again. If the test fails, so you was previously passing, now it fails, we say that the mutant was killed. Right, so, and killed is green here because killed is good. You count that mutant. You want to catch all the mutants. But if the test was passing, you apply a mutation, and it's still passing after that, that mutant survived, it lived. Your test is not sensitive to that mutant, which not always is a bad thing. Like killing mutants is always a good thing, but sometimes your test, the mutant will survive just because that code is unreachable or any other criteria. So we need to take this analysis in hindsight. But the whole point is when you run several mutations across your entire test suite, you can measure the quality of the test suite by how many mutants it kills. This is a mutant coverage metric. Should we set a target for that? Guess what? No. Hopefully you got that point. Okay, but at least this will give you a baseline to filter which are the low-hanging fruits, which are the tests that are more vulnerable, or the ones that you're suspicious of, oh, this is not really testing anything, right? Let's see an example. So this one is, we're going to take the divide function and reverse the if conditional. And here, I have this in the code, so we're just going to come here. I'm the mutation suite now. I'm just going to say here, I'm going to reverse that conditional, save it, and run the test again. You should be seeing here that I have two fails. One fail here, one fail here. The first one is because I expected a no, not receiving an error, and then I got an error, which is correct because I reversed the if condition. In the second one, I removed the guard, the panic guard, so I let the code run through here, and I got my division by 0. So in this case, both tests fail. By mutant testing terminology, both mutants were killed, right? So this is first mutation. Second mutation, I choose to change a different part of the code and replacing the division operator with a multiplication operator, and I'm going to run the test suite. So here I'm running the test. Oh, actually, I need to do the mutation first. Done. I'm going to run, and the test is passing. How is that even possible? I'm making this exactly opposite operation. It was multiplication and division. They're opposite. Of course, I choose this. That's why I choose this test case very carefully, because 1 multiplied by 1 is 1, and 1 divided by 1 is 1. That's why exactly they have the same result. But this is just to prove a point. Remember, toy project. So based on this, we have the following test results for my mutation test suite. Mutation number 1 was killed by both tests. So this is good. This mutation was caught by my test suite. Mutation number 2, as you've seen, it passed. So the mutation survived, and this is essentially a bad thing. My mutation score for this suite is 50%. We can fix that, of course. We need to have a better test case that where multiply 1 by 1 is not a very good case. But we're going to fix that in a moment. The question we need to ask this first is, can we do this in Go instead of me manually editing every single line of code, adding a mutation, run the test suite? The short answer is no. Unfortunately, we don't have anything out of the box to do that for us. But we have the next best thing. We have ASTs, and we have a very good standard library to help us manipulate that. I'm not going to get into the details because we had a good talk yesterday talking about compiler. For the point I want to make, the only important thing you need to consider is that ASTs are an intermediate representation of the code sitting between text and binary formats. So the code is, by compiler magic, becomes AST, and by a bit more magic becomes the binary. And this is a sweet spot for us because this is a representation that we can easily manipulate with code, as in this example. So imagine you have the binary expression a plus b. The representation using the standard library AST package is just ast.binary expression. I have one operand a, other operand b, and I have my operation, my token add. So you can see by this, this is a screenshot of the standard library. X is the left operand and Y is the right operand. We don't really care about position in this case. I'm not going to get into that, but of course, for other things, it's important. If I want to do a mutation and use the AST package, I can simply change the value. So in this case, I'm taking the operator and changing from addition to subtraction, as easy as that. OK, this is the base tool. So how do we kill mutants with Go? First step, load the code from disk, parse the code to AST format, apply the mutations, write code back to disk, run Go test, profit. And this is what we're going to see in the next demo. So let's go step by step. I'm going to close a bunch of things here. And the first thing we need is to load the AST. And everything is using these 3 packages from the standard library: the parser, printer, and token. I just take a file name. I'm hard coding a few stuff here just to make this code simpler. But I'm taking div.go. I need to create a new file set. This is just part of the AST API. And I'm going to parse the file name div.go into this file set. And this is an AST.file, which is the root of our AST that represents that particular file, my div.go. Here I'm just creating a new file with the same name in the subdirectory mutations. And I'm using the printer standard library package to print the AST back to disk. So I can run this. Let's see. This is, I say go run main go. This should have generated a file in my mutations directory. Is div.go is there. Let's look in VS Code here. And you can see it's exactly a replica of the file I had before. And you can say, oh, you're just lying to me. This is not real processing. So I'm just going to add a comment here. I'm a comment. And you can see, so I'm parsing here. Let's just run again. And you see that my comment doesn't appear in the mutation file because this is not parsed by default. I can actually change the behavior of how I want to parse some things. I have a few possible flags here. In this case, I can add the parse comments here. And if I want the comments back into the file, I can just do this, run again, and then now I have my mutation with my comments. So you have a few ways to control that library. But for the purpose we have here, we don't need any of those things. We just want to make a few changes to the file. So the next step is, OK, I can parse, I can write it back. Now I need to be able to apply modifications. And luckily, we have this AST util package in the tools library that provides us with this very helpful function that's called AST util apply. And that will take a node, a root node of an AST, and it will allow it to pass 2 parameters. First parameter is a pre-function, which, if you remember, AST is a tree, so it has a pre-order traversal and a post-order traversal. So here I'm just passing new. I don't want to do any modifications in pre-order, but I want to modify in post-order because I want the modification to happen after I parsed out the child. In this case, I'm passing this reverse if condition. And here, the rest of the code is the same, and this is how I'm expressing my mutator. So I have a cursor, and from that cursor, I can get the node I'm currently exploring. I'll do a type switch to see if this is the kind of statement I care about. In this case, oh, it's an if statement. And here on the if condition, I'm just inserting a man in the middle that is an unary expression with the operator not over the same condition. And I'm returning false. So this signature, the return value, what represents is that if I return false, it stops parsing my AST. If I return true, it will continue to do and parse for the next occurrence of it. Of course, in real code, you would like to have some clever rules here to decide how many mutations you want to do, if you want to keep mutating or not, and choosing the right functions to mutate, and so on. This is just an example. So I'm just finding the first one and interrupting the parse immediately. I have another mutation here that's the same thing, but change the binary operator. So I'm looking for a binary expression. And if in my expression it's a quotient operator, I'll replace with a multiplication. So let's run the first one. So this is hard code to reverse the conditional. I'm just going to see here 6 mutations, go run main go. And you see that my file here in the mutations have the not divided by 0. If I replace this with the, oh, well, wait, let's run the test and see it's the same effect. Oh, of course. There's a challenge here that I put the mutation in a different folder, so this will never catch. So if I want to really test this, I would need to manually replace this file here, which I won't do now because we're going to fix this in the next step. Okay, cool. So we can have one mutation. Now let's do the other one, which is change binary operator. Let's go run. And my mutation now, this is back to normal, and I have my multiplication. Okay, so I have a way to mutate files. Now I need to be able to run the Go test properly. And let's have a look at how we can do this in this next example. So here, what I'm going to do is add some logic here too. So I did the mutation. I'm going to call run tests. I have this helper function that will basically run Go test and return the results of Go test in this parsed structure. It's just a slice of test events. And I'm going to range over these results and basically filter out, because this output is quite verbose. I only care about is if my test passed or failed. So I'm filtering out a few things. And just for the sake of showing, so what run tests do is take a directory, and they'll just call exec go test --JSON to make it easier to parse. And if it fails, remember, if the test fails, this will return an exit status of 1. I'm just logging, I don't care. Move on, parse the results, and this parse function is my helper function that will convert the format of JSON to this test event structure. So I have this nice in a way that I can extract only the properties I want. So let's go here, look at the tests, and say go run main. And you see, I have both passing. Because this is running on my non-mutated code, in this case, it's just running here, this normal code and normal tests. This should be passing. If you don't trust this is actually running Go test, let's break this test. Now there's a different result, and this should be fail exit status 1 as expected. So the final piece of the puzzle is, okay, I don't want, like, imagine I want to run the test on the mutation, not on my actual code. So how can I do that in a very easy way? I don't want to be dragging and dropping code or making copies. There is a compile trick we can use, which is called overlay. And an overlay is a file like this that has a replace directive. And I can use that to say, for this file, replace with this other file. And it's super neat. I can simply go here and say, let's use go test for now. So I can say go test. It's passing verbose because I want to see it. So these are the normal tests. Here in this folder, I have already a mutation that's the diffuser. Let's just do like manually the mutation here, because I know this is going to break. I'm doing the reverse if conditional mutation. So normal go test, but if I say -- overlay and pass the overlay.json, now I have my panic. Now my test is failing because now it's replacing at compile time that div file with the mutated file. Now we have all the pieces of the puzzle. We can simply go here and do a bit of manipulation. So I'm basically creating this translation function just to get the right terminology. If a test is passing, I'm going to call it survived. If a test is failing, I'm going to call it killed. And I'm generating the overlay here with my replace directive. I have some helper function just to write this JSON file for me. And I just need to change the run test function that now it adds this dash dash overlay with my overlay file, and we're done. So what we can do now is say which mutation we're running first. Of course, in a real project, this will be configurable, but we don't have time for that. So go run mango. And first scenario, if condition, both mutations were killed. And the second scenario is change binary operator. We can run again. Both mutations survived. Finally, we have something that looks like a mutation tool, and let's fix that test. Let's fix that test because it's annoying me. So let's see, this is 4. I'm checking 4, so I have 8 divided by 2, and then I'm going to run again, and now at least one of my tests caught that mutation. That mutation was killed, as you can see here. Oh, sorry, I didn't pay enough attention to the captioning. Okay, that mutation is killed, and let's get back to our tools. So this is a toy project, of course. I did some research in what's out there in the open source community. The most mature tool we have today is called Gremlins. It has been not very much updated, but it has some recent commits, like from 2 months ago. But most of those other tests are kind of abandoned for a few years. But still, it's nice to see how the community got so far. Also, I tried to add my own implementation of it. This is the last one is just a toy project, like just one, very similar, the code. But I think instead of fragmenting the community, maybe we should converge to one of those. I think Gremlins is the most cool one, at least. It's very few things is more satisfying than saying Gremlins unleash on your code base. And of course, some takeaways is write tests for the right reason. Do not, even if your CI encourages you to game the system, remember their insurance policy. You don't want to bet your career on bad tests. We just show how choosing your test inputs can affect your test sensibility. So choose your inputs wisely. In the ideal world, this was just like an unit test, a single case. Test table-driven test, lots of inputs, trying edge cases, corner cases, so on. This is super important. One mutation alone is not enough to tell you if a test is good or bad. We always should look things in hindsight. And of course, if you get your full test suite and you see that suddenly you have a test that survives every single mutation you throw at it, then yeah, you have a suspicion on that you might need to investigate if this test is what we call a weak test and is not testing anything properly. But of course, performing all possible mutations is also very expensive. But which gives me hope is that so is fuzzing. And fuzzing is something that we managed to add to the compiler very recently. And in this case, this particular test case that I use like 101, fuzzing would also flag that test if we had like a bug in the code. So there is some overlap between fuzzing and mutation in this sense. But mutation has its own strengths by itself. And I think mutation test in Go is not yet mature, as you can see, but we have everything we need to make it happen. It's just a matter of do we as a community want that, yes or no? And hopefully, I believe that I'm on the yes team. I think that we should make this happen, but it also depends on you. That's it from me. Thank you, everyone.